my TTL computer. For the next series of videos, we're going to take a look at operating the computer. And today we'll be looking at manual operation and programming of the computer. And next video, I think we'll take a look at something I haven't mentioned before, which is a bootload process I've developed and a ROM capability. And we'll look at that in the next video. And then after that, I think we'll take a look at the software development stack, if you will, that I've put together so far. And that'll be working, implementing programs on the laptop using the assembler and the hex loader. Okay, so today we're going to develop a simple program that's just going to be a counter that's just going to be in a loop, and will count from 0, unbounded up, and it will just overflow and reset and continually do the counting. So I thought we'll take the opportunity to kind of introduce some of the hardware elements that we really haven't spoken about to date. And we start out with our clock over here, and we have the ability to run the clock in either single step mode, low speed mode, which is 2 hertz, high speed mode, which is 500 hertz, and I've also been able to implement up to 625 hertz. Seems to be our limit. And this is our manual clock switch that will clock one time. This is our this will halt the clock. And then over here we have this will display our program counter. It will show on the bus display our program counter switch. This will display our A register on the bus. This will reset the program counter, and this switch will allow us to load the program counter with whatever we have set up on our data switches. And over here, we look at our memory adjust register input switch. We have our RAM in switch, and we have our RAM display switch. We also have our step counter display is shown here, our step counter reset, and we have our reset switch for our control unit and our UART, and we'll talk about how that's used really when we look at the bootloader. We also have our program and run switch. So right now it's in program state. Switch that to the left would be in run state. And then we obviously have all of our data input switches. And those are activated with the leftmost switch. We'll enable these. So we really want to make sure that we are in program mode when we activate the switches, so we don't have a situation where we have bus contention, where we have some of the other circuitry that's driving signals on the bus, and then we're also driving signals from the data switches. We don't want to be doing that, obviously. And then so those were kind of all of our input elements. And then our display elements, we have just our clock signal indicator. This is the negative clock cycle. This is the positive clock cycle. We have, again, our bus display, which will show whatever is being what's out on the bus. We have our memory adjust register display. Again, we have our step counter display, and this is our instruction register display. And we also have the output display, or the digits display. And again, these LEDs are not being used anymore, but they showed the state of the control signals. I'm not really using them. Again, I don't think it's very valuable at the higher frequencies, but I may yet re-enable those by putting in a a buffer chip to drive those, but it's not really a priority, and it's something I just might do later on. Okay, so those are kind of all of the elements of the hardware. Most of the chips are synchronous chips that have been used. So what that means is you really have an enable signal that goes to the chip, and then the chip will change its state with the positive edge of the clock. So you'll see that behavior as we go through the programming cycle. You'll see that I enable an item, and then we'll clock the it'll hit the clock signal, manual clock signal to change the state or enter the register value, whatever we're doing. But we'll see that as we go along. Okay, so this is the program that we're going to be doing today. It's just a simple program where we're going to. Now, this sheet is a spreadsheet I put together for actually a different project that maybe we'll look at sometime for a different computer, but it allows me to do simple programming just in the spreadsheet. We see here all of the instructions that we have in our instruction set as it stands right now. Add memory, call. Hex is a special function for working with hexadecimal numbers. We have the in statement from the UART, jump if no carry, jump if not 0, load A immediate, load B immediate, load A from memory, load B from memory, output to the UART and the display at the same time. We have the return statement, we have store A and subtract. So that's our instruction set as it stands now. And again, so we're doing a simple counting program. So we're going to load A immediate. Here's our opcode value, and here's the data. So we'll be loading A with a 0. Load B immediate. Here's the opcode with a 1. We will output that to the digits display and the UART. We're not so concerned with the UART, but that's what it would be doing. The hardware would be doing. Output that to the display. We're going to do the add operation, which adds register B and A together. So that will increment our A register, and it stores the value, the result back to A. And then we'll jump back up to the display instruction, which will output the incremented A register to display, and then just goes through our sequence again. Anybody that's built any kind of hardware like this, it's really easy to put together a spreadsheet like this, and it makes it much easier to program your computer. It helps out a lot where we have the addresses are here, the memory address that you were working on, the opcode just helps to keep things in sync, and also helps obviously when you're doing the programming. Okay, so that's what we're going to be doing, and I'll just use that as a cheat sheet for myself to enter the program. All right, so as I said, we're already in program mode. Here I'm going to do the program counter reset. I'm going to clock that just reset the program counter, and I'm going to reset the step counter. All right, so we're in programming mode. I'm going to enable the switches now. Remember, we have pull-ups on the bus. So when there's nothing driving the bus, that goes up to all highs or FF. I'm going to enable the switches, and that'll get pulled down right now because our switches are enabled. So we'll just see how that works. Take them back down. All right, so we're at 0, and we already reset our program counter, but here's our memory address display. So that's still got garbage data in it. So what we want to do is 0 that out to get back to memory location 0. So we are going to enable that right, and then we clock that in. So now our memory address, we're at address 0 now. Okay, so let's start entering our program. So we are going to start with load A immediate, and that is 1001. and we are going to clock that data. Here's our memory address we're working in. We're going to clock that into the RAM, and that's been clocked. I'm going to disable the input switches, which means the bus is floating again now. I can press the RAM. We're working with address 0 in the RAM, and we can just display the RAM. And there's the value that we just entered. So you can do that to check the values. I kind of don't do that anymore when I do the programming. All right, so I'm going to re-enable the switches. So now we're at address 0. And remember, we're in 2-byte instruction words now. So that was just the first, we entered the opcode. Now we need to enter the data. So the data is going to be at, the opcode's at address 0. The data is at address 1. So we want to clock that into our memory address register. So now we're at address 1, but we want that to be 0, right? Because load A, we want to initialize that to 0. So we clock that in. Now we need to go to address 2, right? And it's convenient to look at the memory address register just to help keep us in sync with what we're doing. So we want to go to address 2 now, clock that into the memory address register, and we are up to load B immediate, and that's 1010 is load B immediate. So we want to clock that in. We want to go to address 3 now. We want to memory address register is at address 3, and we want the opcode for, we're loading B with 1. So we want to load that data in. Okay, now we're up at the next address, which is 4, I guess. We want to clock that into the memory address register 4. Now we want to do the output command, output A register to the display, which is, that's the opcode for the out. And we want to clock that into RAM. Now we are at address 5. I want to clock that into our memory address register of 5. And here's where we do the add operation. And add is 100. Clock that in. Now we are at address 6. Clock in memory address 6. And that's our jump instruction. So we want to do jump. We want to clock that into RAM. We're at address 7. Clock that into the memory address register, address 7. Now this is the where we're jumping to. And we are jumping to memory address 100 to loop back to the output instruction. So that's our address that we're jumping to. Clock that in. Okay. So if we didn't make any errors, our program is entered. All right. So what we'll do now, our clock is disabled. So we'll switch to run mode now. Now the bus is floating. When we're in run mode, the control unit is basically disabled and is not feeding any of the control signals. So once we re-enable, we go into run mode, the controller is now taking control. And we'll see that the things will start to change. So that'll probably get pulled down with the program counter value. All right, so we're back. Now we're in run mode. We want to reset the program counter back to 0. We want to reset our step counter. All right, so now we're ready to run. Our program counter is at 0, and our step counter is at 0, and we're all ready to go. So what we'll do is we'll start out by stepping through the program. So we're in a single step. So right now, we're going through the fetch phase. Here's our load A immediate instruction has just been fetched. it's still not into the instruction register yet. We just clocked that. Now that instruction is in the instruction register. Now we see the program counter has been advanced. Now, so we just accessed the first opcode as memory address 0. Now we're going to memory address number 1. And we know that memory address number 1 has 0 because we're loading A with 0. Okay. Now we're at memory address 2. This is the load B opcode. It's still not in the instruction register yet. Now it's clocked into the instruction register. Program counter has been advanced. Now we're at memory address 3. And that has our 1 because we're loading B, the incrementer, with 1. So our next memory address, 4, I guess that is. That's the out instruction to the display. 5, memory address 5. And that is the add command. We see that gets clocked into the instruction register. That's actually the result of the add, 1. Right? We had 0 and now we're at 1. This is memory address 6. That's our jump instruction. That's been clocked into the instruction register. Now we go to memory address 7. That's the memory location we're jumping to, 100. I could say 100, it's not really 100, but it's really 4, but it's 100, so I say 100. So we're jumping to 100. We have our jump instructions here. And now we see the next instruction we're executing is 4, or the 100, as I said. You'll see that will come into the memory address register, and that's the output to the display. And we should see 1 here now, and we do. All right, so there we went through the cycle. We entered the program. We switched to the run mode. We single-stepped through the program to kind of see how that works. And now we can switch to 2 hertz mode. So this is just running at 2 hertz a second. So you see we have our counter going. All right, let's drop that down. Let's go up to 500 hertz. So we're at 500 hertz now. Okay, we could halt the system by halting the clock. We could switch back to 2 hertz. All right, so now the clock is halted. We just clock it again and it will resume where it left off. Okay, so that's the basic operation of the computer. We introduced all the input elements and our display elements and how we use those. I might just quickly point out while this is running all the different elements that make up the computer, because we kind of really haven't done that. So we have our clock. This is a logic unit and some glue logic for controlling the register loads. This is just a bus driver for the display. This is another logic chip for control signal logic. This is our memory address register. This is our RAM. This is our instruction step counter. This is our instruction register, the control unit. These are shift registers that drive the 16 control lines. And obviously the controller uses that. This is our UART for serial I/O. This is just the bus driver for the switches. This is a bus driver chip for the program counter. These 2 chips make up our program counter. The high byte and the low byte of the program counter. This is our A register. This is another just glue logic chip. This is our ALU. This is our output display register, and also handles the logic of driving the digits display. This is a 7-segment driver for the display that the ALU is using. So this whole section makes up the output register and the display logic. We have just 2 transistors that are being driven by the display chip to do the multiplexing, and the display chip implements the output register. It also decodes the register value and into BCD, and then feeds that into the 7-segment display driver, which is then again multiplexed back and forth through the 2 transistors. So in a nutshell, that's it. That's all of our hardware. I'll talk a little bit more about some of these chips, because some of these again are implemented as using microcontrollers, and I'll explain that in a separate video that kind of recaps things and compares this hardware to some of to Ben Eater's computer and a couple of other TTL computers, how this differs and where I think that there are benefits and drawbacks to this approach. But the last thing here is this is a 4 megahertz crystal clock that drives all of the chips that are microcontrollers, which is basically that drives the control unit, the UART, the ALU, and the output display chip are all driven from that. So that's also the reason why as we speed up the clock, that we start to run into issues with the controller, where I said it takes a certain amount of time to execute the procedural instructions that implement the combinatorial functionality of that combinatorial functionality of the controller, is because increasing the clock frequency does not change the frequency that the microcontrollers are working at. So that's a fixed frequency of really 1 megahertz, because these chips divide the clock frequency down to 1 megahertz. So that's where we get a problem where we're increasing the frequency, the speed of the computer, but the speed of those microcontrollers is remaining constant. So we can have an issue there. All right, so that's it. I hope that was informative and kind of showed you how to use this hardware. You could see it's very cumbersome using the switches to do the programming, and it's even more cumbersome now that the computer is in 2-byte instruction mode, because you have to really keep track of what you're doing, and taking two memory locations to implement an instruction. It just gets to be very tedious and error prone. So it's a huge improvement to be able to use the hex loader and develop the programs on a laptop and load them up. It's still good to have this capability. If you're doing some small testing of some things, it's a lot easier to just do it with the switches and single step through the execution of the instructions. It's just still beneficial to be able to do that. Okay, that's it. Thanks for watching.